Hello everyone and welcome to the Ben's Chem Videos Sunday night live stream. In this live stream we are going to pick up right where we left off with our discussion on chemical equilibrium. Thank you very much for being with me here today. If you are new to the stream, then welcome. If you are returning, then welcome back. So without further ado, we are going to jump right into chemical equilibrium. As always, your participation is highly encouraged, whether that's leaving your thoughts in the form of messages in the chat, or better yet, you can call into the show via Discord. There's a link right down there in the description. Another thing is I have created a new playlist called Chemical Equilibrium's Live Streams, which includes not only the first Chemical Equilibrium volume, last week's live stream, but will also include this one as well when the live stream is recorded and uploaded into a video. All right, so let's go ahead and get into this. This is Chemical Equilibrium Volume 2. So, as I do with all these live streams, I like to just do a quick, ideally quick, recap of the previous live stream. So, in this case, that was Chemical Equilibrium Volume 1. So, here is a short bulleted list of all the information that we discussed last week. So we defined the term chemical equilibrium, also known as dynamic equilibrium. Dynamic in the sense that it's always changing. You have products becoming reactants, you have reactants becoming products in this back and forth type process. And of course, equilibrium is the condition at which the rates of the forward reaction, i.e. reactants becoming products, is equal to the rate of the reverse reaction, i.e. products becoming reactants. So it's important to remember that the equilibrium says nothing about how fast the reaction is, only how far the reaction has proceeded once the rates of the forward and reverse reactions are equivalent. Another important thing about equilibrium is that the concentrations of the reactants and products at equilibrium do not have to be equal. But if we want to know any relationships between the reactants and products in a chemical reaction at equilibrium, we define the term the equilibrium constant, which is represented by a capital K, not to be confused with the rate constant, which is denoted by a lowercase k. And we arrive at this expression here, where we have the equilibrium constant K is equal to the product of the concentrations of the products C and D for this reaction above, raised to the power of their stoichiometric coefficients, divided by the product of the concentrations of the reactants A and B, raised to the power of their respective stoichiometric coefficients. So that's the formula for the equilibrium constant. We also talked about the significance of the equilibrium constant. What does the value of the equilibrium constant imply about a chemical reaction? And basically, if K is very, very small, that means you have a reactant-favored equilibrium, high concentration of reactants, low concentration of products at equilibrium. If the equilibrium constant is very, very large, much greater than 1, then you have a product-favored equilibrium, which proceeds almost to completion, where you have a high concentration of products relative to reactants at equilibrium. And if you have a value of K that is close to 1, then you have a reaction that proceeds about halfway from reactants to products. So that's the significance of the equilibrium constant. The other thing we talked about in great detail was manipulating chemical equations. So oftentimes as chemists, we have to manipulate chemical equations, whether that's reversing an equation, multiplying an equation by a factor, or adding equations together. So we talked about what to do with the equilibrium constant in all three of those cases. If you reverse an equation, you invert or take 1 over the equilibrium constant. If you multiply an equation by a factor, you raise the equilibrium constant to that same factor to arrive at your new equilibrium constant. And then finally, if you add 1 or more equations together to arrive at an overall reaction, then you multiply the equilibrium constants of the reactions that you're adding together to arrive at the equilibrium constant for the overall reaction. And then finally, what we talked about was the equilibrium constant in terms of pressure, which is K sub P. If it's concentration, sometimes it'll just be called K, and other times it'll be called K sub C. So we have Kc and Kp. We were able to use the ideal gas law to derive a formula for how to convert from Kc, the concentration in terms of, or excuse me, the equilibrium constant in terms of concentration, to Kp, the equilibrium constant in terms of pressure. And I'm going to move myself out of the way so that you can see this formula. So this is the formula that we derived for if you have a equilibrium constant in terms of concentration, how to convert it to that same equilibrium constant in terms of pressure. And of course, this applies only to gaseous reactants and products, where we have Kp, equilibrium constant with pressure, is equal to Kc, the equilibrium constant for concentration, multiplied by the quantity of RT. R, of course, is the ideal gas constant, 0.08206 liters times atmospheres over moles times kelvins. And T, of course, is the absolute temperature in kelvins. That whole term raised to the power of delta N. Now, delta N, that is simply the sum of the coefficients for your products minus the sum of your coefficients for the reactants. So there's another thing here where this is a fairly important graphic here. So this describes basically, if you start out a chemical reaction, what happens, a reversible reaction, what happens over time. So this particular chemical reaction, we have hydrogen reacting with oxygen to form water. And it's at this point that I'd like to say that in the last live stream, I made a terrible mistake. I forgot about the 2 in this water here. So when I showed this chemical equation last week, it was shown with an understood 1 in front of the water, which is incorrect. That would not result in a balanced chemical equation. There should be a 2 here, so I have corrected the mistake and put a 2 there now. And I also pinned a comment on that video asking anybody if they could spot the mistake that I made to call it out what they think it is. And one person by the name of Jacob Halber guessed it correctly. He identified the mistake that I made. I promised to make a sulfur hexafluoride shout out to anybody who correctly identified the mistake. And so, Jacob, since you answered the call, this one is for you.
Thank you very much for correcting me, Jacob. I wholeheartedly appreciate it. And that goes for anybody in here. If you would like to correct any mistakes that I've made, I would greatly appreciate it. Thank you very, very much. All right, so moving on, we have this situation here in which we start out with nothing but reactants, in this case hydrogen and oxygen, and we allow them to react together. The concentrations of these two predictably decrease over time. Likewise, the concentration of your product water increases over time to the point where eventually the rates of change of these concentrations for the reactants of products flatten out, and this is the point at which we call dynamic equilibrium. That is when equilibrium has been established. So notice again, this is another thing that I talked about before, where equilibrium does not imply that your concentrations of reactants and products are the same, just that they're the same, the rate of change is the same. So in this case, we have this equilibrium here where the concentration of water is much higher than that of hydrogen and of oxygen. The other thing, of course, is that equilibrium does not imply anything about the speed of a chemical reaction. This reaction might take forever to get to products, but again, it doesn't say anything about speed. It's talking about how far the reaction has proceeded once the rates of the forward and reverse reactions are the same. So anybody has any questions about that, feel free to leave your thoughts in the chat, or like I said before, you can call in via Discord. Okay, so I think we are about ready to move on to the new content. So here we go. So the next thing that I'd like to talk about is something called heterogeneous equilibria. So let me move myself back where I belong here. Here we go. Just drag myself down to the corner. There it is. All right. So what is a heterogeneous equilibrium? Notice that the word equilibria is shown up here. Equilibria is just the plural form of equilibrium, right? I have one equilibrium. I have two or more equilibria. So a heterogeneous equilibrium is an equilibrium reaction in which one or more of your reactants or products is a pure solid or a pure liquid. So for instance, in this chemical reaction, we have gaseous HCl reacting with gaseous water to produce liquid, or excuse me, gaseous oxygen to produce liquid water and some chlorine gas. So this is an example of a heterogeneous equilibrium. So the question on my mind is, if we wanted to write an expression for the equilibrium constant for this reaction, how would we do it? And I think at this point, this is a good opportunity to go to the whiteboard and see if we can write an expression for the equilibrium constant for this reaction. So we're going to go ahead and go to the whiteboard. I'm going to go ahead and paste the reaction equation here. All right, so let's say we wanted to know
what the equilibrium constant is for this reaction, right? That would be K, I'll just call it Kc, equilibrium constant with respect to concentration. Well, if we apply the law of mass action, which is the relationship between equilibrium constants and concentrations of reactants and products, we would be inclined to conclude that the expression for the equilibrium constant is going to be the concentration of water, H2O, raised to the second power, because there's a coefficient of 2 in front of it, times the concentration of chlorine, Cl2, also raised to the second power, because it also has a coefficient of 2, divided by the concentration of HCl raised to the fourth power times the concentration of O2 raised to the first power, or simply just the concentration of O2. So this is what we might expect to be the correct expression for the equilibrium constant for this heterogeneous equilibrium. However, I am here to tell you that this is incorrect. Why is it incorrect? Well, the reason why it's incorrect is because, in this case, water is a pure liquid, right? Its concentration does not change over the course of this reaction. The concentration of pure liquid water is determined by the density of water, which is constant at a constant temperature, right? And so the lesson here, the very important thing to understand, is that when you have a heterogeneous equilibrium, right, when you have a reaction in which one or more of your reactants or products is a solid or a liquid, you must omit them from the equilibrium constant expression. So what we're going to do is we're going to take this water term here, and we're going to simply erase it. We are going to remove it from the expression for the equilibrium constant. And so what we arrive at is this, which is correct, where we have the concentration of chlorine squared divided by the concentration of HCl to the fourth power times the concentration of O2. So this is the correct expression for the equilibrium constant. So make sure that if you are encountering a problem like this on a test, that you always pay attention to these little states of matter that are located in the parentheses, right? Because they matter. They're important. Sometimes we overlook them. Sometimes we kind of let them pass over our eyes and we don't really pay attention to them. And we're mostly just concerned about the chemical formulas, but in this case, the states of matter are very, very important. And they could be the difference between a correct and an incorrect answer. Okay, so that's heterogeneous equilibria. If anybody has any questions about that, please feel free to drop them in the chat or call into the show. And by the way, if you are finding value in this stream or this video, and you'd like to reciprocate value, please feel free to drop a thumbs up on this video. And if you're feeling super generous, maybe consider sending a super chat or donating through Streamlabs if you happen to be watching live. All right, so let's get back to the good old chemistry content, shall we? Okay, so we talked about heterogeneous equilibria. Let's move on. So the next thing we're going to talk about is how to calculate the equilibrium constant for a chemical reaction with measured equilibrium concentrations. So let's say you carry out an experiment where you have a reversible chemical reaction. You allow that reaction to reach equilibrium. You measure the initial concentrations before the reaction and the concentrations of that reaction at equilibrium. How could you use that information to calculate the equilibrium constant, right? We have a message in the chat that says, from Hussein O'Day, it says, "Hey Ben, can you upload this video later?" Yes, I certainly will. And you're welcome to check back and watch it anytime you like. It'll be on my channel page. You can also watch it on my playlist called Chemical Equilibrium Live Streams. This will, once it's uploaded, it will end up in that playlist. So thank you very much for your message, and thank you for being here. I certainly, truly appreciate it. All right, so we're talking about calculating the equilibrium constant K for when you're given measured equilibrium concentrations. So this example right here, I'm going to drag myself out of the way. Here we go. Hussein says, "'Cause you explain the bread and butter of chemistry." Oh, I think that's a compliment. Thank you very much. Appreciate your kind words and your feedback. Okay, so this is an example of an experiment in which we have this equilibrium reaction up here, where we have hydrogen with reacting with iodine to produce hydrogen iodide, right? And so basically what every row of this table represents is an experiment in which the initial concentrations of hydrogen iodine and hydrogen iodide are sort of different from one reaction to another. So The important thing to notice here is that the equilibrium constant is always the same throughout. It doesn't really matter necessarily what the initial concentration is. Notice that the initial concentrations can differ from one experiment to the next, and as a result, the equilibrium concentrations will differ from one experiment to the next, but they differ in sort of this linear fashion where the expression for the equilibrium constant, or the value of the equilibrium constant rather, always ends up being the same thing, which in this case, for this reaction at this particular temperature at which this reaction is being run, is the number 50. So I say temperature because temperature does have an effect on equilibrium constant. The equilibrium constant does have a temperature dependence to it, and we'll elaborate on that more in a later live stream later on down the road. But you can see here, these are all just examples in which this reaction has been started and then allowed to reach equilibrium, and no matter what the initial concentrations that you start with are, the value of your equilibrium constant, which in this case is the concentration of Hi squared divided by the concentration of H2 times the concentration of I2, that value always ends up being the same. The equilibrium constant does not depend on the initial concentration. That is, if you're controlling for the temperature. So everybody still with me? If you're not, I would hope that you would let me know in the chat or the comments. Okay, so we're going to move right along, and we're going to encounter this little, whoops, let's see, I accidentally moved the wrong thing. Move myself down here, there we go. All right, so we're going to go through this problem here. So it says consider the following reaction where we have 2 moles of methane gas reacting to form 1 mole of ethylene gas, and that's the C2H4, and 3 moles of hydrogen gas. So the reaction says, or the problem says, the reaction mixture is initially composed of methane with a concentration of 0.245 molar, and then it says at equilibrium, the concentration of ethylene, C2H4, was measured to be 0.075 molar. And we're asked to calculate the equilibrium constant with respect to concentration for this reaction. So in that previous slide that I showed you just a moment ago, we had all of the equilibrium concentrations, and so to find the equilibrium constant, it's as easy as just plugging them into the formula for the expression of the equilibrium constant, and that's pretty easy. Bingo, bango, bongo, punch them in the calculator, and you're done. This problem is a little different. In this problem, we're given the initial concentration of the only reactant, the methane, CH4, and we're given 1 equilibrium concentration, the concentration of C2H4, and we're supposed to find the equilibrium constant. So we're not given all of the information that we were in the previous slide. And the question is, can we still use the information given to find the equilibrium constant? The answer to that question is absolutely yes, we can. And the tool that's going to help us get there is something called the ICE table. So let me move myself out of the way. I'm going to resize myself a little bit just to make sure I'm out of the way. So the ICE table is a tool, it's an acronym, it stands for Initial Change Equilibrium, is a tool to sort of help you keep tabs on the progress of a reaction to equilibrium. So basically you populate the ICE table with the values that you know, and you try to use the table to determine the values that you don't know. So what we're going to do is we're going to use an ICE table to solve the problem in the previous slide. So if you give me just a moment here, I'm going to cruise on down to the whiteboard, and while I'm here, I'm just going to, well, first of all, delete everything from that previous problem, and I'm also going to copy the ICE table, and I'm going to copy the problem, and we will solve it. So copying the ICE table, so it's a little small, I'm going to resize it. That's probably a good size. I'll just stick it up there. And the problem itself, let me see if I can go ahead and copy that. Let's see. Okay, we have that. And I'm going to resize it. And okay, so everybody should be able to see this. Again, if there's any confusion or any concern, by all means, drop a message in the chat. Let me know what's going on. Okay, so we have this reaction, methane reacting to form ethylene and hydrogen gas. So basically what we're going to do is we're going to populate this ICE table with the values that we have and the values that we don't have. So basically what this is doing is it's keeping tabs on the concentration of every single reactant and product throughout the entire process. And I'm trying to erase something. I'm trying to erase these guys up here, but I don't seem to be able to do that. So I don't know why I can't do that. Suppose I've never tried to do this before. Maybe there's a different way. Maybe I can lasso. Nope. Okay. So, man, I thought I had an easy way how to do this, but let's see. So, all right. So I'm just going to go ahead and let's see. Is there a white marker? That would be cool. Maybe I can gray it out. Let's resize it. Thank you for bearing with me, guys. Just dealing with my technical difficulties here. I'm trying to erase these generic concentrations and replace them with the actual chemical species that we have. So anyway, so what I'm going to do is I'm going to set up a row up here where I'm going to include the concentrations for all of these individual chemical formulas. So so we have 3 of them. We have one reactant, we have 2 products. So we have CH4. Let's see, black. I want you to be black. Okay. We have CH4. We have C2H4, and we have H2. Right? So whatever piece of information that we know, we're going to populate with this table. So the problem tells us that the initial reaction mixture is composed only of methane and that its concentration is 0.245 molar. So this CH4 here, initially it's 0.245. So that's all we have at the very beginning, which means the initial concentrations of C2H4 and of H2 are both 0. And the other piece of information that the problem gives us is that the concentration of C2H4 at equilibrium was measured to be 0.075 molar. So C2H4 at equilibrium is 0.075 molar, right? So that means, I'll do this in a different color. I'm kind of running out of room because I'm writing a little bit big, but that means that the change, right, of this C2H4, it went from 0 to 0.075 molar. So that means the change must have been positive plus 0.075 molar, right? And whatever amount that the concentration of one product increases by, the other product must also increase by that same number. It must. So in other words, since this increased by this much, then the other product, the H2, must have also increased by that much. But it's also important that we take stoichiometry into account. So notice that in this balanced chemical equation, for every 1 mole of C2H4, we have 3 moles of hydrogen. So that means that whatever concentration, whatever amount that the concentration of this one, C2H4, changed by, the amount of H2, or the concentration of H2, must have changed by 3 times that, right? And so if you take this 0.075 molar and multiply it by 3, right, because we have 1 mole of this stuff and we have 3 moles of the H2, if we multiply that by 3, we end up getting a change in the case of hydrogen of plus 0.225 molar. And again, that just reflects the stoichiometry of the reaction, right? Because there's a coefficient of 3 in front of that hydrogen. That means for every 1 mole of C2H4 that's produced, 3 moles of H2 are going to be produced. So whatever amount that this concentration changes by C2H4, we have to triple it to get the same amount that the other product, the H2, increased by. So since the hydrogen concentration increased by 0.225 molar, that means that its concentration at equilibrium must be 0.225 molar, right? And in the case of the methane, the reactant, well, there's a 2 in front of it, so we know the concentration is going to decrease. The question is, by how much is it going to decrease? Well, in this case, it's going to it's going to decrease by twice the amount that the concentration of C2H4 decreased. So basically, whatever the change is, you multiply that by 2 in this case, because there's a 2 in front of that CH4, and we get minus 0.150, right? And this kind of makes sense intuitively if you think about it, right? If you have a reaction that starts out with nothing but reactants and you allow the reaction to proceed, the concentration of your reactants will decrease, the concentration of your products will start to increase until they reach somewhere in the middle at equilibrium, right? And so we can calculate the concentration of methane, CH4, at equilibrium by simply taking the initial concentration, 0.245 molar, and subtracting away the change, which is 0.150 molar, and we end up getting an equilibrium concentration of 0.095 molar. And I've just noticed that I've put the letter M for some of these, but not all of them, but they're all supposed to be molar. So I think the sensible thing would have been to remove the M. But anyway, a couple of messages in the chat real quick. What are your advice to ICHO students? I guess my advice to anybody would be work hard, study hard. I'm sorry, I don't know what ICHO means. Forgive my ignorance. Devara says, hello, sir. Hello, right back at you. And then Hussein says, Ben, you're a great chemistry teacher. Why you only post your videos 3 years apart? We need more of you. We love you. And sorry for disturbing. Oh, no problem at all. Thank you for your kind words. Thank you for your feedback. The reason for my inconsistency over the years is kind of personal, and I am not ready at this time, I guess, or I'm not prepared at this time to spill more details on that. I'm just trying to shock things back to life and get back to being consistent. So anyway, all right, so let's get back to the problem. So now we were able to, knowing the stoichiometry of the reaction, knowing the initial concentration of the reactant, and knowing the equilibrium concentration of just one of the products, we were able to find the equilibrium concentrations for all three of these chemical species, of our reactant and of both of our products. And the ICE table is kind of what helps us do that. So at this point, what we need to do is to just simply calculate the equilibrium constant, since now we have all the equilibrium concentrations. And so Kc is going to be, well, the expression would be the concentration of C2H4, that's our first product, to the first power, because there's an understood coefficient of 1 in front of it, times the concentration of H2, and we're going to cube that because there's a coefficient of 3 in front of the H2, and we're going to take that and we're going to divide it by the concentration of CH4, and we're going to square that because there's a 2 right there, right? So now it's just a matter of simply, I'm going to make this a little bit thicker. There we go. Now it's just simply a matter of plugging in the values that we have and plugging them into a calculator and calculating the number, right? So concentration of C2H4, that's 0.075. We're going to square that, or no, we're going to leave that alone. The concentration of H2, that's 0.225, and we're going to cube that, and we're going to divide that whole thing by this 0.095, which we are going to square. So this is kind of a big expression. If you type the whole thing into your calculator, make sure you're using your calculator correctly. I've said this before and I will say it again. You do not want the first time you're using your calculator to be on test day. You want to make sure that you understand how to use parentheses, how to use fraction bars, how to raise things to a power. Make sure you're taking into account the correct order of operations, and you will be happy that you familiarize yourself with your calculator ahead of time. So the number that I got when I performed this calculation, and feel free to correct me if I'm wrong, but I think it's correct, the number that I arrived at for the equilibrium constant for this reaction is, where is it? 0.095. So that is an example of how to calculate the equilibrium constant for a reaction when you're given the initial concentration of the reactants and the equilibrium concentration of just one of the products. You can deduce everything else using the balanced chemical equation, and it's the ICE table, initial change equilibrium, that helps you do that. Some people will call this a RICE table. They'll put like another R up here where they'll actually have their reaction equation at the top. I don't do that. I think ICE is cooler than RICE, so I just go with ICE table and just put everything up there. So all right, so that is an example. And like I said before, if you have any questions, please feel free to drop them in the chat or call into the show. I'm going to check real quick, see if anybody's called in. Nope, nobody's called in. All right, we can proceed. So we are going to go right back to the PowerPoint. All right, here we go. So the next topic that I want to discuss is a little thing called the reaction quotient, which is denoted by a capital letter Q. So the reaction quotient is, you can either define it with respect to concentration or you can define it with respect to pressure. If it's concentration, then it's going to be the concentrations of the products, which in this general reaction scheme are C and D raised to their coefficients, lowercase c and d, divided by the product of the reactant concentrations A and B raised to their stoichiometric coefficients. And for the reaction quotient with respect to pressure, it's going to be the same thing but with partial pressures. Now, you might be asking yourself, well, how does the reaction quotient differ from the equilibrium constant? So far, Q looks exactly like the equilibrium constant K. I mean, these expressions are the exact same thing. And the answer to that question is that the reaction quotient is calculated at any point in the reaction, right? Whereas the equilibrium constant is only for when that reaction has achieved equilibrium. So the reaction quotient is calculated not necessarily at equilibrium, but the equilibrium constant is always calculated at equilibrium. And the nice thing about the reaction quotient is that the value of the reaction quotient compared to the equilibrium constant can help you predict the direction in which a reaction is going to go. Is it going to react more to form products, or is it going to react more to form reactants? Which way is it going to go? Well, Q can tell you that. So, for instance, there's a little graph that I've made here, and let me drag myself over here just to get out of the way. There we go. Okay, so this graph represents a very simple, generic equilibrium reaction where we have one reactant A reacting to form one product B, and there's 1 mole of each, and we've made the assumption that the sum of the concentrations is equal to 1 molar, just to keep the numbers very simple. And so the reaction quotient in this case is simply going to be concentration of B over concentration of A. Again, it takes on the very same formula as the equilibrium constant. It's just that it's not at equilibrium, and the equilibrium constant is at equilibrium. So in this reaction, the equilibrium constant is 1.86. That represents this blue line here, 1.86. So that would represent a point in the reaction where the concentration of the product B is like 0.65 and the concentration of A is 0.35 or something like that. So the equilibrium constant is 1.86. And so according to this graph here, if the reaction quotient is less than the equilibrium constant, well, that tells you that the reaction is still product heavy and it needs to react more to form reactants to reach equilibrium. So if Q is less than K, then that means that the reaction will proceed to the right. It'll proceed in the direction of products. Conversely, if the reaction quotient is greater than the equilibrium constant, then that means that the reaction will shift toward the left. It'll go in the direction of the products. The concentrations, or the reactants rather, the concentrations of the reactants will increase and the concentrations of the products will decrease if Q is greater than K. So Q helps predict the direction in which the equilibrium reaction is going to go. Is it going to go toward reactants? Is it going to go toward products? All depends on the relative values of the reaction quotient and the equilibrium constant. So with that in mind, we're going to do a problem, and I'm going to move myself out of the way here. Sometimes I forget to move myself out of the way, but I think in this stream I've done a pretty decent job of it. So it says, consider the following reaction where we have N2O4 reacting to form 2 moles of NO2, and it has an equilibrium constant of 5.85 times 10 to the minus 3. And the problem tells us that the reaction mixture has the concentration of NO2 is 0.0255 molar, and then we also have some N2O4 in there coming in with a concentration of 0.0331 molar. And the problem asks us to calculate the reaction quotient, Q sub C, and determine the direction in which the reaction will proceed. So let's go ahead and take this problem to the whiteboard. So if you give me just a moment here, I'm going to start by erasing all this junk from the previous problem, and I'm going to copy the new problem over there. So here we go. Almost got it. There it is. Just need to resize it. Okay. Can everybody see that? I think you can. Maybe I need to make it a little bit bigger. That looks like a pretty good size. Okay. So we need to calculate the reaction quotient, and we need to use that information to determine the direction in which the reaction will proceed. So all we have to do is just plug the numbers into the formula to get the reaction quotient, and then compare the value of the reaction quotient compared to the value of the equilibrium constant, and that will help us determine whether it's going to go to the left in the direction of products, or if it's going to go back to the right in the direction of reactants. So in this case, we have Q sub C. That's going to be equal to the concentration of NO2 squared divided by the concentration of N2O4. Again, this is the same exact expression, same exact formula for equilibrium constant. The only difference is that this particular reaction at this particular moment in time is not at equilibrium, right? And so numerically, what does this look like? Well, NO2, that's going to be 0.0255, and we're going to square that, and we're going to divide that by N2O4, that's 0.0331. And as always, you are more than encouraged to bang out this calculation for yourself. I encourage that because sometimes I make mistakes in my calculations. I still don't have a scientific calculator. I mean, I used to have like 3 of them, but I've looked all over my house and I can't find one, so I have to use the limited functionality calculator on my phone to bang out these problems, or just the calculator app on my computer. But anyway, enough stalling while I wait for you to figure this out. So the number that I got was, where is it? Okay, so it's 0.0196. Again, y'all, please let me know if you've gotten the same thing. So now, since our original equilibrium constant is represented in scientific notation, in order to compare our reaction quotient to it, I think it would be important to put this in scientific notation as well. So I'm going to go ahead and do that. So that would be 0.0196 would be 1.96 times 10 to the minus 2, right? Because we move 2 decimal places to get to 1.96. So all right, so we've calculated our reaction quotient. We've expressed it in scientific notation. The only thing left to do is to compare it to the value of our equilibrium constant. So 1.96 times 10 to the minus 2. Is that less than or greater than our equilibrium constant, which is 5.85 times 10 to the minus 3? Well, 10 to the minus 2 is greater than 10 to the minus 3, right? 10 to the minus 2 is 0.0 something, and 10 to the minus 3 is 0.00 something, right? So in this case, in this particular problem, the QC, is greater than Kc. And as we saw a moment ago, if the reaction quotient is greater than your equilibrium constant, that means that this reaction will proceed to the left. It will go in the direction of the reactants. The concentration of the reactants will increase. The concentrations of the products will decrease. So that is an example of a problem where you might be asked to calculate reaction quotient, and then based on that value, determine the direction where the reaction will go. All right, so I'm going to bring it back to the PowerPoint real quick. And all right, so we did that problem, and I am going to go ahead and end the educational part of the stream for now. The reason why I'm ending it here, it might seem a little abrupt. The reason why I'm ending it here is because the next topic, the next block of information is going to be really big. We're going to do some fairly complex problems that are going to have very, very long solutions to them. So I want to make sure I start with that so that we have more than enough time to cover all of that content. So next week, what we're going to talk about is how to find equilibrium concentrations. So you can think of it as like the opposite of what we did tonight. So tonight we did some examples where we found the equilibrium constant given initial and equilibrium concentrations. Next week, we're going to do the opposite. We're going to be given the equilibrium constant, and we're going to be asked to find equilibrium concentrations. So again, those problems are a little bit more advanced, and some of them even use the quadratic formula, which I'm sure we all remember from our algebra class. But I'm really excited to do that, and it's going to be probably a very lengthy live stream, and hopefully it provides value, just as I hope I provided value tonight. So all right, I'm going to end it here. Thank you guys very, very much for watching. I wholeheartedly appreciate your being here, your contributing to the chat messages, and your potential future super chat donations. No pressure, but hey, you know, I would certainly appreciate it. All right, guys. Thanks everybody again. I hope you've had a great weekend. I hope you're geared up to have an amazing, productive week. Thank you very much. Like I said, you can refer to the playlist, Chemical Equilibrium live streams. That's where all of my volumes of chemical equilibrium content will be. So that's it. All right, you guys, take care.